We are going to start our talks, which will be all about deforestation, afforestation, and forest management with Max Nova, who is the founder of SilviaTerra, a small team of foresters, biometricians, and programmers dedicated to enabling precision forestry. SilviaTerra is one of the grantees of Microsoft's AI for Earth program, and I'm really welcome to have Max, who's graduated with a CS degree in Yale University, to talk about forest and machine learning and the way towards precision forestry.
Great. Well, really appreciate you having me in here today. Can you hear me okay?
Yes.
All right. I'm going to attempt the screen share maneuver here. All right. Is this coming through for everybody? Well, great. Well, yeah, appreciate you having me on here today to talk about forests and climate and data, because that is where I live. So my name is Max Nova, and I'm one of the founders of SilviaTerra. And for the last 10 years, we've been working with many of the largest commercial landowners in the United States, government agencies, and conservation groups to figure out how to integrate remote sensing and machine learning and big data into their forest inventory and management process, trying to figure out, where do we cut, where do we plant, where do we build roads, where do we fertilize, really at sort of the place where the rubber hits the road in terms of forest management and data. And so I wanted to share some of the things that I've learned over the last 10 years working in this space, especially as it relates to climate. Yeah, let's get into it. And I wanted to begin actually with sort of a surprising chart that was surprising to me, at least, when I saw this last year. So this shows U.S. economic growth and then consumption of a variety of raw materials, including timber and paper. And so you can see the dark line for GDP goes up and to the right, sort of like what we would expect. So does consumption of these raw materials. But then what's really surprising is starting in the late 70s, there's actually a very clear decoupling of GDP and population growth from the consumption of these raw materials. And this is extraordinary. This is so remarkable. Like, this is a story that I think does not get nearly as much press as it needs to get. Population going up, economy going up, total timber consumption, not per capita, total timber consumption, total paper consumption going down. That's an unbelievably optimistic story for the climate, and one that I hardly ever hear discussed. And because we're talking about large scale climate action and having people change the management of their forest, it's just really important to have this macroeconomic context and sort of understand where we're at. This chart actually comes from a great book by MIT economist Andrew McAfee, came out last year, about the dematerialization of the global economy. And we actually see this in forests right here in the United States. So this is the total forest inventory of the United States, and then the harvests. And what's surprising to a lot of people is that in the United States, we're growing more trees than we're harvesting. The total biomass in forests in the United States has been going up for decades. Actually, this data only goes back to 2008, but this story has been true for decades, and that's really a remarkable phenomenon. And so now where we fit into this is, like I said, we're providing remote sensing based forest data to these managers to help them figure out how to optimize their forests for a variety of economic and sustainability outcomes. And so, like I said, we've been doing this sort of project by project for a decade. And about 2 years ago, we started working with Microsoft and their AI for Earth program to scale up what we had done sort of project to project and run that across the entire United States to generate what we call Base Map, which is the first ever high resolution forest inventory of the whole US. And that's really exciting because it allows us to do things like this, where for any property in the United States, you can draw it on a map and then get a report about the forest that's on there. So not only do you get the species breakdown on the forest and sort of this acre resolution heat map of where the volume is across the property, but you can actually drill down even further and get the diameter distribution by species. And that's never been possible before. This is sort of like a Zillow for trees, which you would think in 2020 that exists, but until we did this, it didn't exist, which is really exciting. But it's exciting not. I mean, the data is good, but what we actually care about are all these values in the forest, things like timber, things like wildlife habitat, things like carbon, things like wildfire risk reduction, all these values that are present on every acre of the forest. And to have data about those is exciting because it means we can begin to benchmark what we have and pay people to get more of what we want and measure that that's actually occurred. So for this talk, I'm going to be very focused on carbon and paying people to change their behavior to increase the amount of carbon on their forests and how data and machine learning plays into that process. So the most famous of these markets is CARB, the California Air Resources Board. The forest carbon version of this has been around for about a decade. $1.8 billion of California ratepayer money has gone into paying for forest carbon offset projects. There's also CORSIA, which is coming up. This is EU airline carbon neutrality legislation. And then, of course, there's plenty of voluntary commitments in the US through this We Are Still In Pact and other voluntary commitments internationally. And so the intent of all of these programs is very good. You know, it's people that are trying to do the right thing when it comes to offsetting their climate impact and increasing the amount of carbon stored in forests. Unfortunately, a lot of sophisticated buyers are beginning to lose confidence that the way these forest carbon protocols are structured right now actually creates real change on the landscape. James Temple at the MIT Tech Review has done a particularly good job of digging into this. There's a couple papers that have come out of Berkeley, and there will be additional ones out of Stanford this summer that sort of get into some of the structural issues with how we're measuring and paying for forest carbon and some of the adverse selection that occurs there. And so now at SilviaTerra, over the last 4 years, we've been involved in, I think, 18 of these forest carbon offset projects. And so we've sort of seen how the sausage gets made, and we really sit right where the rubber hits the road. And in, you know, through that perspective, we've sort of gone back to first principles and said, you know, well, things aren't accomplishing the outcomes that we want right now. And sort of at first principles, what should we want from our climate action? And I think ultimately it's very simple. So we propose this RISE framework, which says we want to, you know, we should be using data and all this technology to achieve a climate impact that is real, that is immediate, that is scalable, and that's efficient. And so I'll walk through sort of briefly what I mean by each of these things. So real, at the most fundamental level, this means when you pay somebody for the carbon on their property, are you actually creating real change on the landscape, or are you just paying somebody to do something that they were going to do in the first place? And so for something like planting trees, this is actually very easy to assess, right? You know, if there haven't been trees on a property for a long time and you plant trees, then it's clear that you've changed somebody's behavior through a payment. It gets trickier though on these harvest deferrals and avoiding deforestation and things like this, where you have to actually assess what the landowner's intent was going to be. You know, was this landowner likely to harvest this acre of timber? Luckily, the field of timber economics is very mature, and it's actually very straightforward to construct these net present value curves like I've shown here. And all this is saying is that, you know, as your tree gets older and grows more, it becomes more valuable until at some point its growth rate drops below your financial discount rate and the net present value begins to decrease. And this is what drives commercial forest management in the United States. You harvest when your net present value is optimized. And while this is a fairly trivial curve to construct, what's not trivial is getting all the data to inform this. It depends on market prices. It depends on the sizes and species of trees on your property. It depends on the merchantability specs in the area. It depends on your distance to mill. It depends on all sorts of things. And this is where machine learning and big data and AI can really play an important role in having these much better assessments of what the business as usual and the harvest risk on every acre is, because that's a critical component of creating real change on the landscape. The second consideration is immediacy. And so an easy way to think about this is, you know, we're in a climate emergency, and so we should be trying to maximize our immediate climate impact this year. And this is where these afforestation and tree planting projects sort of run into trouble, is when you plant a sapling this year, at the end of this year, how much carbon has that sapling pulled out of the atmosphere? The answer is not much. You know, and afforestation is a super important part of the overall forest management toolbox and the fight against climate change. But in the area of immediacy, you know, it takes these trees decades to begin to accumulate meaningful amounts of carbon. And on the right side, you see, actually, this picture got cut off. This is out in Stanislaus forest here in California. My co-founder is cut off at the very bottom of this enormous tree. But you know, this is where these avoided deforestation projects can have a real immediate impact, just because the amount of carbon that you're dealing with is so much greater right off the bat. And so if you can avoid having that tree get harvested, that's actually an enormous immediate climate impact. Another consideration is the scalability. This is really around how many acres can you engage in this climate protocol. And this is where existing forest carbon projects tend to fall down because the measurement and monitoring costs are so high that only really large landowners can participate. You know, you have to have 5,000 plus acres. So it tends to be corporate owners, it tends to be tribal entities. Who it doesn't tend to be are small private landowners. And this is especially important in the United States, where you can see the light green on this map. You know, that's small private landowners. These are people that own, you know, 400, 500 acres or less. And they actually own the bulk of forests in the United States. And so it's critical to be able to include them. And this is where machine learning and AI, when you can measure every acre every year and include these landowners, it makes an enormous difference in the potential scale of impact you can achieve. And then the final consideration is efficiency. And so stated most simply, how can we maximize our climate benefit per dollar of cost? Because there's a lot of things we can do to pull carbon out of the atmosphere. There's a lot of different acres that we can approach, but every acre is different. Each one's going to have a different cost. How do we prioritize this? How do we put our money to the lowest cost carbon on the landscape? But this is actually a trickier question than you would initially think. Like I talked about earlier with the net present value economics of forests, you know, forestry is sort of weird because it takes decades to grow trees. And so if you're not accounting for the time value of money and discounting those costs back to the present, you know, you have to do time discounting of money when it comes to forests because the time periods are so long. And so you need to, I put all caps, the present cost, because you have to discount those costs back. But where a lot of people get tripped up is that you actually have to do the same thing with carbon and the climate benefit of your action. And hardly anybody thinks about this. I think this is one of the biggest gaps in climate thinking right now is the time value of carbon. The World Resources Institute is one of the few people that's put out anything reasonable about this. But intuitively, it makes a lot of sense. You know, if I could sequester a ton of carbon today or a ton of carbon 100 years from now, which one's more valuable? Of course, it's the carbon today. But this is the time value of carbon is a way of quantifying that intuition. You know, and there's a lot of assumptions that go into this. We sort of fall back on using the EPA's social cost of carbon so that we don't have to fight any of those holy wars. But you know, it is a critically important thing to account for when you're doing carbon accounting if you're trying to be really serious and really real about achieving climate impact. And so this is where we come in, and this is where you know, the AI community in general can play a really important role. Is that, you know, if we want to pay people to change their behavior, that's a market, and measurements make markets. It's critical to have reliable measurements that underpin all of these transactions, so that buyers can have confidence that when they pay somebody to change their management, they actually get a real change. And so that, you know, this is what we've been working on with Microsoft here in the United States. To do, and this is actually forming the basis of what we call the natural capital exchange, which is a method to pay landowners for short 1-year term harvest deferrals, where we're analyzing every acre every year to assess what the business as usual is. Any landowner can participate. It's weighted by their harvest risk, and we just pay them to not cut, and we update our forest inventory data set every year to verify that they haven't cut. And, you know, to achieve a durable impact, you just run this year over year over year over year. And because we're able to target, you know, that top of that net present value curve, where the cost per ton of carbon is very low, this is orders of magnitude more efficient than many other types of forest-based climate action. And, you know, this isn't just a theoretical thing. We ran a pilot with Microsoft last year in Pennsylvania to do this, to sort of prove out this concept, and now we're doing it across the whole U.S. South here in 2020. But, you know, so this is a very brief presentation. You know, 15 minutes there's a lot of moving parts here. It's very complicated, but it's really exciting because I think there's such an opportunity to use data to do a much better job of achieving a real, immediate, scalable, and efficient climate action today. We're actually putting out a white paper about forest and carbon. I would be happy to send out a advanced copy of that to anybody on this call. Just shoot me an email at max@SilviaTerra.com. And yeah, really excited to be here in this community, and looking forward to continuing the conversation. So that's me.
Thank you so much for that terrific talk, Max. That was really exciting. And I can already see in the chat that there's so many questions coming up. I just want to briefly mention that we are going to have a panel session after this talk session with all the speakers. And so Guys, don't worry. We see your questions and we will keep them until the end and ask them in the panel for sure. So speaking of afforestation and planting new trees, our next speaker is Simeon Max, who is the environmental impact officer of Lab at ETH Zürich. And his work on reforestation actually in Indonesia won him a Google Impact Challenge in 2018. He graduated with a forest management degree from Technical University of Munich, and I'm glad to have you speaking about your work at Lab and on reforestation.
Thanks very much, David, for this beautiful intro. I'm going to share my screen now. Can you actually see my shared screen?
Yep, all good.
Great, thank you. The atmosphere is incredibly thin. It's analogous to the rubber around the balloon. And each year we emit about 10 gigatons of carbon into the atmosphere. That's like 37,000 Empire State Buildings. Some of this carbon goes into the ocean, some into the land, but the result is that the atmosphere has over 300 extra gigatons of carbon and growing. This excess is warming the climate and oceans, leading to disruptive and dangerous changes. Cutting these emissions is the highest priority in the fight against climate change. However, we also need to start drawing down some of that extra carbon that is already out there. This requires an immensely powerful tool. For the first time in history, our lab, the Crowther Lab at ETH Zurich, was able to provide a quantitative understanding about the climate mitigation potential of the restoration of forest ecosystems. In the first step, however, we needed to count how many trees there really are on the planet. We combined satellite imagery with data from the ground to be able to look below the canopy and describe the vertical structure of the forest, linking this to environmental variables, temperature, moisture, soil characteristics. We detected patterns and used machine learning and AI to extrapolate these across the globe. The result? There are about 3 trillion trees on Earth, which store approximately 600 gigatons of carbon. So the next question is, how many additional trees could there be? And how much carbon could they store? In essence, what's the potential of forest restoration? So we looked for the land areas that could potentially support trees and where forests would naturally grow. The research is based on the measurements of the tree cover by hundreds of people in 80,000 high-resolution satellite images from Google Earth. Artificial intelligence computing then combined this data with 10 key soil, topography, and climate factors to create a global map of where trees could grow. This map of restoration potential is essentially the areas of degraded land, with potential for greater tree coverage, where agricultural, urban lands are already excluded. In total, this is approximately 0.9 billion hectares. And this is immense. It's an area larger than Brazil, which could fit approximately 1 trillion additional trees. And we estimate if those 1 trillion trees reach maturity, which of course would take some time, they could store an additional 100 to 200 gigatons of carbon. Relate that figure back to the 300 gigatons of excess carbon in the atmosphere today, you can see that we now have scientific evidence for forest restoration as an immensely important tool in the fight against climate change. What is missing now to make that real? Restoration is still limited by data to unlock funding and to build the restoration knowledge, which will enable all of the tree planting organizations out there to be more successful and to scale their work. In the worst case, the areas that need to be restored look somehow like this, possibly even competing with other human land uses. These ecosystems have been deprived of their ability to naturally regenerate. at least not on a time scale to make a difference. Ecological restoration is difficult. Practitioners rely on a time-consuming trial and error approach, and projects anecdotally report survival rates as low as 20 to 30% in the first years of operations. History is basically littered with examples of restoration gone wrong. Apart from the social, economic, policy, and land rights challenges, a lot of manual work, time, and financial investments are necessary to restore those areas. New knowledge on ecological restoration pathways, which also rely on indigenous know-how, are needed to help nature back on track while respecting the social and economic needs of local people, something which this photo cannot even depict. Out there on the ground, there are already many restoration organizations that struggle to find the best solution for their ecological challenges. And we speak to them. We're building a global project database, and we want to understand their struggles. And these are some of the questions we hear from our restoration partners. What are the right species for this land and for my goals? How do I maximize carbon storage, but also care for biodiversity? Where should I prioritize my investment for the biggest impact? What will happen with altered conditions due to changing climates? And how should I manage my land, fertilize, or get rid of invasives? On the other hand, there is science with a wealth of know-how already at our fingertips, and we have the methods and tools to advance our understanding rapidly. But there is a disconnect between the agglomeration of knowledge in academia and the restoration practitioners on the ground with all of their questions. And it's obvious that a lack of widely available restoration knowledge is one huge obstacle to advance the restoration movement and to solving the global climate and biodiversity crisis. Connecting questions and answers requires a two-way communication. So rather than building global models from satellite observations, we rely on all of the people, scientists, researchers on the ground and the data that they collect on their ecosystems. We use this information to inform the satellite observations, which can then be used to extrapolate the patterns across the globe. Using this combination of approaches, we can get really interesting insights into the structure and functioning of ecosystems around the world. Rather than focusing on one or two parts, we study the entire ecosystem as a whole, including everything from the microscopic organisms in the soils, all the way to the biggest trees and forest cover. All of these organisms interact with one another and facilitate the functioning of the ecosystems. So we have set out on a quest to bridge the knowledge gap by building a restoration knowledge hub in lines with recent political and corporate tree planting pledges. We want to hand out the latest ecological science and motivate even more initiatives to start restoring. We're interpreting science to action and the needs from the field back to our impact data scientists. Now, the data we have is quite reliable on a global scale, but when you zoom in further and when you want to look at the individual pixel, the confidence decreases and the pixel size is still not fine-grained enough to make a plot level conclusion. More and better data is needed. We are therefore developing a tool to incentivize data collection based on mutual benefits for science and practitioners. And this tool must be scalable, easy and cheap to make it usable for everybody. Because if you do restoration right, nature is able to recover quite rapidly, as shown here on this 2-year-old reforestation plot in Indonesia. If someone monitored these trees, so collect the data on diameter and species and maybe also tree height, the restoration world would be able to learn from this success story. Smartphones are the data collection tool, so why not in reforestation? Together with the DS3 lab at ETH Zürich, we aim to develop algorithms that will detect basic tree data from nothing more than a photo. So our man or woman on the ground takes a photo of a tree with a reference object, in this case, a standardized credit card sized card, because that's just available in most of the households around the world. The training data is used to teach the neural network the segmentation of photos for the diameter detection and to learn identify the tree species from the colors and the structure of the bark. Recurrent measurements of the same trees enable us to create species-specific growth curves and also correlate these with a set of environmental variables to compare growth speed of various species compositions across sites. And of course, we are also recording the GPS position of every photo to build global tree species distribution models. Digital data potentially provides added value for everybody. The data taken in the field enters a positive feedback loop. As we receive more data from the ground, we can improve each of our layers and refine our models to give better recommendations to the practitioners. There are currently billions of people in the world who more or less directly depend on nearby forests for their survival. And most often they only have little say about their natural resources. The data in their hands, in their smartphone, will return ownership to the local forest stewards and will enable them to participate in sustainable and green economies that are based on their natural resources. Everybody else in the restoration value chain can benefit, not least from the added transparency and traceability of products or ecosystem services, such as carbon, for which there is an increasing demand from industry and individuals, as we just heard. And I leave it up to your creative minds to think about the full potential of this data in the restoration value chain. Better forest restoration data clearly benefits all restoration stakeholders and has the potential to accelerate and enhance the restoration movement to eventually help us grow the 1 trillion trees. Thanks very much. I'm happy to take your questions now or later. Feel free to shoot me an email if you want to connect.
Thank you so much, Simeon, for that wonderful talk. And I'm sure there will be many questions later for the panel. So we are really excited how that goes. Finally, the last talk of today will be jointly given by Janina, who's a postdoc at ETH Zürich's Environmental Policy Lab, which is affiliated with the Department of Humanities, Social and Political Sciences, as well as the Department of Environmental System Science. Her research focuses on sustainability governance and what role states, firms, NGOs, and other actors play. She's giving the talk together with Sam Levy, who's a PhD student at also the same lab, at Environmental Policy Lab, and his focus is to evaluate and understand the impacts of large-scale commodity agriculture on natural ecosystems and human well-being. He currently works in Brazil and Indonesia on deforestation. So please welcome the speakers.
Thank you so much.
Yeah, thank you. All right, I will share my screen. Great. So thanks for the introduction. Today, myself and Janina will be talking about how machine learning can help prevent commodity-driven deforestation. And so, as was mentioned, I primarily work in the Brazilian Amazon, and Janina primarily works in palm oil in Indonesia. So we'll both be giving examples that reflect our personal research. And the other thing to note is that neither of us are machine learning experts, but rather we're social scientists who work with big data and think that our added value to this talk today is that we can give insight on what is relevant for interdisciplinary social scientists like us to address these big questions. So the reason why I'm talking about commodities is that commodity production is the largest driver of deforestation globally. It's about 27% of all deforestation is for commodities. And this trend is much stronger at the tropics, where biodiversity and carbon is concentrated. And when I'm talking about commodities, I'm really talking about four things: beef, soybeans, palm oil, and pulp and paper, which are with beef and soybeans primarily grown in South America, and palm oil and pulp and paper primarily grown in Southeast Asia. Now, consumers are connected to all of these by companies that process, transport, and refine these goods into the daily goods we all know and consume, such as this, McDonald's, Big Mac, and fries. The reason why these companies are important and the supply chains are important is partially that it connects all of us consumers to tropical deforestation, but also the actual number of companies that do this processing and transporting are very consolidated, which makes an action point for NGOs and governments to try and change the behavior of these companies, thereby changing entire supply chains and protecting forests at scale. And these companies are also exposed to a huge amount of deforestation risk, which is increasingly cutting into their market value. So there's actually a lot of motivation for them to adopt policies that will see their risk exposure reduced. And what these policies look like is that a company like Nestle sets a policy outlining their position on deforestation, and they will choose a mechanism such as banning producers that deforest, certified production, or supplier engagement. And then this will filter down a supply chain through the traders they buy from, all the way down to the farmers, who should therefore change their practices and reduce the deforestation. And that's the theory behind these policies. And the number of these policies is increasing rapidly. So this is actually a little bit out of date, and the increase since 2014 is about 60%. So 508 companies have now committed to a supply chain policy to end deforestation. But this doesn't tell us anything about the rigor of these policies or their real world impacts. And this is really where our group, the Environmental Policy Group, wants to understand what's going on. And what I mean by that is, are these policies effective at reducing deforestation without increasing deforestation in other supply chains or regions? And are the distribution of the impacts of these policies equitable? And this is where big data comes in, because companies down the supply chain don't actually know who they're sourcing from, and those close to the producers, this becomes proprietary information, and they actually don't want you to know who they're sourcing from. So I'm just going to give you an example from Brazil to show you how these supply chain policies work. So what you're looking at here is a landscape in the northeast of the Brazilian Amazon, and all these properties in yellow are sourcing to a specific slaughterhouse. And what we're looking at is before this slaughterhouse signed a policy. And you can see deforestation is pretty much evenly spread across properties that do and do not sell to this company. Now in 2009, they started a policy where they monitored deforestation on their suppliers' properties and threatened to exclude producers who deforested from their supply chains. And this is what happened. So after 2009, properties that kept deforesting have been excluded from the supply chain, and properties that had previously been deforesting to continue supplying have stopped deforesting, which sounds great. But this only really tells us that this company has been effective in changing its sourcing patterns. It doesn't tell us anything about how deforestation has changed. Because, for example, this property is probably still producing cattle and selling to a different slaughterhouse that doesn't have a policy. And in fact, this property and properties like it could have increased their deforestation, completely nullifying the impact of these policies. So how can we understand if this policy is doing anything? Well, this is really where we think machine learning comes in. So there are three ways in which we want to understand how these policies work. The first is through accurate and precise monitoring of land use change. So which is, what I mean by this is accurate monitoring of when deforestation happens and where. And the second is we want to attribute that change to specific actors, to go beyond just a deforestation event to the specific land uses that follow. And the third is we want to link those land use patterns to supply chains so we can really say which company was operating where and what the global impacts of this is. So to go straight to monitoring, what you're looking at here is surface reflectance over time in a forest pixel. And you can see in a stable forest, you have a nice pattern of seasonality. And then there's a break, which is a deforestation event, and this pattern changes. you get high reflectance that decreases over time until you get a new equilibrium for a new land use. And you can kind of see this pattern in the pixel data. And what Aravalo did, and what many others do, is they use algorithms such as random forests to automate the identification of these deforestation events. And they do this at a subpixel level, and they do it at scale, which is great. It really helps understand whether these policies work. But we think that machine learning can go further, and the emission and commission errors that are associated with this can be reduced. The resolution that this process is done at can be increased, and the number of land use classes that we understand as occurring afterwards can also be increased.
Exactly, because it's not enough to know where deforestation is occurring. We also need to understand who is driving it and for what purpose. And the availability of higher resolution and higher frequency satellite imagery actually allows us to track a deforestation event over time, so we can see what kinds of land uses follow. However, most of the time, including in this case, which was an application in Indonesia, researchers are still coding these by hand through visual interpretation of this really high resolution data. So they're only able to evaluate a very small share of the images that they have, and have to increase the estimates for national level deforestation drivers by just scaling it up proportionally. This is an ideal example where this could be used as training data to actually have machine learning tools evaluate what types of deforestation drivers are available in different, like at a national level, for instance, but also in specific landscapes, which helps us in two ways. In the first, we will understand whether the types of policies that we are analyzing, which are mainly supply chain and commodity specific. So I focus on palm oil and only palm oil companies. If these companies sourcing palm oil implement their policy, but they're sourcing from a landscape where all of these other drivers, such as mining or forest plantations, are also present, they may just be deplacing deforestation to different types of sectors without making a dent in the deforestation as a whole. Secondly, we also want to be able to attribute deforestation events to specific actors in order to uphold the responsibility that makes these types of supply chain policies work. Because right now what happens is that companies as well as NGOs will try to monitor deforestation on particular properties and exclude suppliers that are non-compliant or punish them, while benefiting and giving incentives to those that are compliant. As an example, this is an NGO called Mighty Earth using high-resolution forestry satellite imagery in one particular concession. And this is a very clear-cut case. We can see the concession boundaries in yellow, we can see the deforestation event in red, and we can also see quite clearly what kind of land use is following because of these rectilinear lines, which indicate that this is actually a large-scale palm oil plantation. Yet, in many cases, it's not as clear-cut, because in the regions that we operate in, you often have overlapping land tenure claims and arrangements, as well as overlapping land use on the ground that may not represent the on-paper attribution of control over the land. For instance, in this paper, here again, they coded individual images by hand and saw that indeed in a lot of large-scale concessions of pulpwood and oil palm, there are actually independent farmers farming independent lots. And this is, we can see this in the small inset image in image B. We can identify those by these irregular shape sizes of the plots. And they're actually associated with a lot of the forest fires, which then will deforest further. And if we didn't know this, we would have attributed this to the company and made the assumption that this is deforestation driven by a large-scale concession. On the other hand, we can also see in the third image that there's a number of plantations that are operating outside of legal concession boundaries, and they might be operating illegally or semi-legally, but still expanding concession and onto possibly priorly forest land. So understanding these types of drivers at a micro scale is important. One, because what currently happens is that a deforestation event will be alerted, and then there needs to be ground proofing on the ground, which tends to happen through companies, which then contact their suppliers, and the suppliers will often provide an excuse such as, this was community-led infringement, we are not responsible, it was outside of our concession. So utilizing this data and the ability of machine learning to really assess this at scale would allow us to understand the credibility of company-led implementation. But more importantly, it allows us to understand whether we're using the right tools to actually address deforestation, because the farmers in the middle will likely not care about the big companies' access to international markets. Rather, they're expanding their plots because of a lack of alternative livelihood options. So that might be a policy arena that it would be more fruitful to pursue to decrease deforestation.
And the third way that we think machine learning can help is by linking these landscapes to supply chains. So I'm going to give you an example from work that I'm doing in collaboration with Trace, a major project by several leading NGOs to try and identify supply chains all around the world, but in this case, cattle in the Brazilian Amazon, and to link slaughterhouses to direct and indirect suppliers to consumer countries all over the world. And the reason why these indirect suppliers, by which I mean a cattle producer that sells to another cattle producer that eventually sells to a slaughterhouse, is that these indirect suppliers are currently not being monitored at all. They're a black hole, and we have no idea how much deforestation they do, and no one's trying to monitor it, including the slaughterhouses themselves. So by using this cattle transport data, we're trying to piece together what's actually happening on the ground, including for these indirect suppliers. So I'm just going to show you an example of this work. So what you're seeing here is one slaughterhouse in the Brazilian Amazon in 1 year, and all the properties that it sources from, both direct and indirect. And those indirect ones are the ones that are far away, which are really across the entire Amazon biome. And through this, we can understand how much embodied deforestation is going into that meat. But we can actually go beyond this, because once we know what property supply to what slaughterhouse, we can link it to a port, and then we can link that port to consuming countries. And that's really important, because these policies actually concentrate in consumer regions around the manufacturing and retailer companies that often make more policies than in the producing regions. And this is a pretty huge undertaking. So that was just one slaughterhouse in 1 year. And this is a network where I've expanded this to one municipality in 1 year. And now we're talking about hundreds of nodes with thousands of links. But for the entirety of Brazil, it's in the scale of tens of millions. And this isn't just a big data problem. This is actually hugely messy data. So the data comes into us as entries on when a cattle was moved to another location. And the name of the location, the name of the farmer, and even the unique identifiers are all corrupted, and they're all messy. And we need to figure out how to link these properties to one another and to landscapes. And for that, we are developing machine learning algorithms, or we hope to link all this data together so we can really see what's happening on the ground.
So in summary, we aim to identify deforestation, classify its drivers, and link it to specific actors and supply chains in as rapid and as high scale of an undertaking as possible in order to really get a comprehensive overview of what these types of policies are doing and how they might be working better. This would then allow us to answer a number of burning policy questions, which include, on the next slide, whether the corporate policies are able to eliminate deforestation from their supply chains and stay true to their promise to consumers that they are taking on corporate responsibility. More importantly, whether they're actually able to influence deforestation rates in a particular landscape and really make a dent in the loss of tree cover that we continue to see happen. Thirdly, from a policy perspective, can we rely on private actors to make rules, enforce, and monitor them themselves, or do we need to have additional aid, for instance, by public policy actors to monitor and implement this? And finally, once we know more about the actual local drivers of deforestation, and specifically whether they're large and small actors, whether they tend to be small-scale farmers, we'll also understand better what the likely implementation of these policies in full would mean in terms of equitable livelihood outcomes if these types of low-capacity actors might be cut out of the value chain and, in the worst case, lose out on their business. And in the policy lab, we work, as we were saying, not only with large data, but also with a number of other tools in a mixed methods framework. This includes also doing interviews along the supply chain to understand from actors involved in it how these types of policies are being translated to the ground. We collect producer level data of producers that are in areas affected by these policies to understand how their market options and their prices, and therefore also their livelihoods, have changed. And we also analyze a number of other types of company level data to understand better whether differences in how company policies are described and also then implemented in practice make a difference. So this gives a little oversight of what the work is that we do in this lab, and we look forward to a discussion to learn together on how machine learning could make it even better. Thank you so much for your attention.